megahertz. Does everybody agree with that? It did it. Y'all with me on this, class? Now, if we do this problem, it's not hard to do this. You might as well just put this here. We're going to look at first the input impedance right here. This would be Zn in port 1. Please note, I'm trying to make sure you understand how to do these things. They're very easy, but if you haven't done this, then I need to make sure you did. If you look at this, and we're looking into port 1, what do I do with Z0? Anybody? How do I go ahead and modify the circuit so I can work with this characteristic impedance Z0 over there? In other words, this thing's going into Z0. Yeah, I'm going to go ahead right now and I'm going to modify this diagram so everybody sees it. I'm going to go ahead and put 50 ohms here. Or I'm going to put Z0. The reason I'm going to use Z0, then you can easily change these things at the end so you've got one equation, you change the values, and you have the solution for every circuit that has this topology. Does everybody understand? We come in here, the input impedance here would be equal to R, you know what, everybody right with that? Plus, and then it's going to be the parallel combination of these two. Does everybody agree with that? Now some of you realize this, it would be 1 over j omega c times Z0 on top. I'm going to do this one time, j omega, or excuse me, it would be equal to, this would be Z0 divided by j omega c over Z0 plus 1 over j omega c. Now I just multiply the impedance here by this and then divide it by the sum. Does everybody understand that? Please write it down. With me on this? Get this. I can go ahead and I can multiply. Now follow me on this. If I multiply this and this by j omega c, now I get R plus, and this would simply be Z0 over 1 plus j omega c times Z0. Convince yourself of that. Take a look at that fraction and go ahead and do it. How many see this right here? In the back, can you see it, Josh? See it? I've taken this right here, this particular part of the equation, just to multiply by j omega c, top and bottom. You get a 1 here, then you get j omega c Z0 here. Is everybody clear on that? I know you had to test it. Now, if I have that, that's Zn1, right? Can we solve that, class? Sure. Is it a complex number, class? Yes. Do you all agree with that? It's a complex number. It's not something we just look at and do. You understand that? You have to feed the values in. But nevertheless, when we have that, if we want to get the reflection coefficient into port 1, assuming it's matched, the reflection coefficient would be, and I'm doing this a different way this time. I'm going to go through it and just put the number, put the equation. It's going to be equal to the impedance we're going into over here, which would be Zn, minus the impedance we came from, which is Z0, over Zn plus Z0. Does everybody agree with that? It's straightforward. It's the impedance you're going into minus the impedance you came from over the sum of those two impedances. That's the reflection coefficient in the port 1, right? It's matched. Do you all agree? In other words, there's no waves reflecting back here. So what is S11? Anybody? What does S11 mean? It is, fundamentally, it's V1 minus over V1 plus when V2 plus is equal to 0, correct? What that means to us, simply stated, is that port 2 doesn't have a signal coming into it. If we look at this, doesn't this have to be equal to the reflection coefficient right here? Because by definition, the reflection coefficient in port 1 is V1 minus over V1 plus. It's the amount of the wave that's incident on that port that's reflected. How many see this? So you have S11, like that. We just punched the numbers. Does everybody agree with this? Are you punching these now, Dan? Yeah. All right, don't do them. Don't give me the answers yet. We'll put them all up at once. Now, that's the reflection coefficient right here in port 1. I don't do this all the time, but this time I'm going to allow you to do this. Because if we want the transmission coefficient through here, so we can get the actual voltage right here. And I'll call that V1 prime, the voltage right here. We know that's a voltage that's important, isn't it, class? I mean, that's the voltage, it's the amount of this voltage, the incident voltage that gets over into this network. Y'all see that, class? Show of hands here, how many do? We covered it last time. We have that voltage, then we just do voltage, excuse me, I got it on the wrong side, it's right here. Once we get this voltage right here, then we can use voltage division to get the actual voltage coming out of port 2. How many see this? I am moving quickly, I know you had a test, make sure you get it. Are you all right with that? Now remember, you want to see this on the exam. Now, where's my man with the iPad making, oh, you got it, okay. He's doing these lectures, and I'm glad he is, because some of you who aren't here, and I'm speaking to you, are going to benefit. If you have this, now I can go ahead and I can get the transmission coefficient into port 1, and that would simply be 1 plus the reflection coefficient. I'm going to warn you about that. That is a complex number. So make sure you write that down. Complex, general. Not always, but usually. That's the transmission coefficient. So now, when I want to figure out, right, and I'll do it right here, if I want to figure out what S21 is, that's V2 minus over V1 plus, or the forward voltage gain when V2 plus is equal to 0. Does everybody recall that? Now really what this is simply, it's how much of this voltage, the incident voltage here, comes out here. It's a transfer function, in other words. You all agree with this, class? How do we do it? Well, this would be equal to, we find the amount of voltage here, right? You all agree with that, class? And that amount of voltage would be equal to V1 plus times the transmission coefficient in port 1 right there. I don't like doing a whole lot of these problems, but I'm doing it for a reason. So many people aren't here or are out of it and haven't done this. Does everybody agree with this? Do you see this, John? Can you read it? Yes. All right. It's going to be this. That's the voltage right here. Now, what do I need to do with that voltage to actually get the voltage coming out here? V2 minus. What do I need to do? Someone. Say again?
Put a resistor on that.
Well, I've already put this equivalent in this port, right? But what do I need to do? There's one particular word that I'm looking for, or something that indicates this. I'm looking at this as a net impedance, right? And I've got this. Isn't this simple voltage division then? When we have the voltage here, it's simply voltage division. So what I'm going to do is multiply this by this impedance, and that impedance would be equal to, if you look at it, and we did that right here. Isn't that the impedance of this parallel combination, class? You all agree with that? If you take a look at this, I'm going to go ahead and take that impedance, Z0 over 1 plus J omega C times Z0, and divide it by the sum of R plus that. Divided by R plus Z0, I'll get out of your way, over 1 plus J omega C times Z0. I hope you can read this. I'll get out of the way. And that would be S21, the value of really the amount of voltage coming out of here. Really, it's the ratio of that voltage to the incident voltage. The voltage leaving port 2 divided by the incident voltage. Is everybody all right with that? Go ahead, Dan.
Is V1 plus S V1 less on this ratio, or is it just?
Well, actually, this is going to divide out. You're right, Andrews. I'm moving a little quick because that would be V1 plus, and this I should have a voltage here that cancels. You're absolutely right. Thank you. All right. Now we've looked into this port. Does everybody agree? Are we done with port 1, class? Yeah. I mean, what could we do? We could do one more thing, and I alluded to this. We could also get one piece of information right here before we leave port one. We could get, and this would first be, well, I don't think I put this down, but I'm going to. I don't know what page they're on in the book, but there's a return loss and an insertion loss. Write this down. This just puts the loss in terms of dB, or the reflection coefficient in terms of dB. The return loss is simply, what symbol does it use for this? RL. RL, and it is in dB, and it is equal to minus 20 times the log of the magnitude of the reflection coefficient of port 1. This would be the return loss at port 1. The insertion loss, all right, going from port 1 to port 2, I'll designate this. This is going from port 1 to port 2. It's how much loss you get in the signal from port 1 as it's transmitted to port 2 is equal to minus 20 times log of the absolute value of S21. Now put those things down. These are very easy to get once you have reflection coefficient, which is S11, isn't it? And you have the actual, if it's a matched system, and S21 is the transmission coefficient. Well, it's not really the transmission coefficient, but it's really the voltage. I call it the forward voltage gain myself. But does everybody understand that? Now these are numbers we can calculate. Here's one thing to know. These are absolute values. They don't have imaginary parts. You'll see that on exams. Got it? Now, we're done with port 1. We have insertion loss, and I'll put that right here. I didn't put it down. This is insertion loss. Insertion loss, and we have return loss. Okay? Now, after that, if we're done with port 1, we turn the thing around, or we look at the other set of terminals. Is everybody all right with that? How many are with me on this so far? Gosh, I'm going to jam that phone one day, because you text more in this class than everybody else combined. All right, now, is everybody with me on this though? I'm going to go ahead and I'm going to have to erase some of this board. Here, resistor, capacitor. This is R, this is C. You know what their values are. Now we're looking at port 2. This is port 1, this is port 2. Now we're doing business at this end. This is Z0. Here, it's coming from an impedance Z0. First thing I want to do, and work with me, class. You should be picking this thing up by now. The very first thing I want, right here, I want to calculate, in order to start this thing off, right at these terminals, I want to get Zn on port 2. That's the very first place I start. Zn port 2. How do I do that? And how about not the first 2 rows, not even the first, wait a second, let's work on the 3rd row. How about somebody in the 3rd row? You got 4 people. One of you is going to cough up the so we're going to help you.
Do you just slap a resistor on the other side for Z0?
All right, that's right. Right here, this, Will?
Yeah.
This is going to be Z0, right? How many agree with that? Now, we look in these terminals right here. If we see that, don't we see a series value right here? So we have that series resistance in parallel with that capacitance, right? Here's what I'm going to do. because I don't feel like I'm doing a whole lot of writing. I'm just going to call, and I'll call it R prime equal to Z naught plus R. With me? Now, I know the impedance looking into those two things looks like a resistor in parallel with a capacitor. How many see that? And I know from what I did before, you may not. Just look at it, write it down. When I do that, this is going to be equal to R prime over 1 plus J omega R prime times C. Now remember, I got that from prior work, the first step. How many remember me getting to that point? Y'all remember that? We had that. That's Zn2. How do I get S11? Now tell me what I'm doing now. I know a lot of you did it. How do I do that? Somebody, wait. No, I'm saving you for last. Everybody in front. How about second to last row? Yeah? How do I do it, Dan? Come on.
So S11.
Wait, couldn't hear you.
That's,
Speak up, because you're live.
It's V1 plus over V1.
Who can help him? Anyone?
Take that, Z, subtract by Z naught, divided by.
Don't you mean S22?
Yeah.
S22, thank you. S22.
That's
Thank
why
you.
we couldn't answer it.
I apologize. Go ahead, Matthew. He at least was speaking up. And, go ahead.
You take the Z into, you subtract it by Z naught, divided by Zn2 plus Z naught. And then you add that to 1.
I think you said Zn2 first, right?
Yeah.
Zn2 minus Z naught over Zn2 plus Z naught. How many agree with that? All right, I've got that. Doesn't that equal the reflection coefficient? That is the reflection coefficient looking into port 2, right? And we know that's the case. If I have that, how do I get the transmission coefficient? I'm going to put it right here. Transmission coefficient into port 2, it really means how much the voltage is stepped up or stepped down coming from Z naught into that network. You all agree with that? What would the transmission coefficient be? Here, I'm going to put it here. Make sure you know this relationship. The reflection coefficient on any port N plus 1 is equal to the transmission coefficient in that port N. All right? So this is simply equal to 1 plus the reflection coefficient in port N. Now, I like doing it this way. I normally say it's 2 times Zn, and there's a reason I do this, Zn2 over Zn2 plus Z naught. I do it that way a lot of times. I'm choosing it to do it this way as long as you know that's a complex number. It's not a strict real. Go ahead.
I hate to ask stupid questions.
No, there is no stupid.
You keep on saying that. Do we need to take the magnitude in polar form and add 1 to that, or do you take the real part in rectangular form and add 1 to that?
Well, if this is a complex number, if you're going to add them, what kind of calculator do you have?
I got an 89, so I can do it either way.
You just put the number in either polar or rectangular coordinates. For that reflection coefficient, it doesn't matter. And go ahead and do the math.
Okay.
Your calculator will take care of it. But it is a complex number, so it has a real and imaginary part. And if you want to do it using a primitive calculator or slide rule, you would add the real and then add the imaginary together. Okay, we have that. We've got this. Now, last part, how do I get S12? Remember, this is going to be V1 minus over V2 plus with V1 plus equal to 0. In other words, you're not energizing port 1. How do I get that? Think about, I know several people did the homework, but a majority did not. How do I get this? And now I'll take it from anyone. Where do I start? Okay. We've got tau 2, don't we? assuming we can actually do this calculation, we got it, right? All right, so we got tau 2. Here we know it's going to be tau 2. And what he's doing here, he's saying that's going to be the voltage as I come from this side. Let's not deal with that one. As I come from this side right here, and I have V2 plus coming in here, that's the amount of this voltage that is developed right here inside this network. So, well, I mean, that tells me if I multiply V2 plus by the transmission coefficient, I get this voltage. Do you agree, class? So you can call this V2 prime, and then I could say this times V1, or V2 plus, that would be the voltage right here. And now, if I want the amount of that voltage that appears here, what do I do? You're absolutely right by that. All right, voltage division, what would it be?
R prime.
I want the voltage here, don't I?
Z naught
Z naught over Z naught plus R prime.
over. No, R prime is Z naught plus R.
Or excuse me, Z naught over R plus Z naught. So, you're right. I'm going to put it as that. Z naught over Z naught plus R. Now, I'm going to get rid of this voltage, but that would be the voltage coming out of the port. Do you agree with that, class? If you energize port 2, this is the amount coming out of port 1. And then if I divide by V2 plus, now I have the ratio of V1 minus to V2 plus, which is that. Does everybody agree? So I'm going to get rid of this right here. And lo and behold, now I have the S-parameter matrix. Now, there's one thing I asked for. Is it reciprocal? So is this reciprocal? Is it a reciprocal network? What do I mean by reciprocal, people? If I take this network and turn it around, do I get the same S parameters? That's what it means. Is it or not? Anybody? You can't tell just by looking at those things, can you? What happens when you work the numbers? Now, Danny, I'll take those values if you got it. S1, what is S11?
We got 0.33 at an angle of minus 1.21.
At an angle minus 1.21 degrees. Is that right?
Yeah.
What about S21?
0.021 at an angle of minus 87.6.
S22?
About 1 at an angle of minus 176.
That would imply a short. I'm not sure I'm believing that one. What is this value right here for Z into? I'll tell you what it is.
R was 100 for the problem.
Z naught's 50. And maybe it's 2 pi times 10 to the 7.
The cavity.
10 to my 7. Did you get
I got 1.59, and that's 93.
That's right. Oh, well, it's real close. All right, I see what you did. You're rounding. You're rounding. You make it 1 at minus, at about minus 176, did you say?
Yes.
Okay, you rounded it. That's not exactly 1.
It's
0.999.
All right. All right, and then what about S12? What do you get for that?
Same as S21.
What does a reciprocal network mean? Now, it says S, yeah, well, all right, S is equal to S transpose. Is that the case for this one? if S is equal to S11, S22, S21, S12, S transpose would be equal to here, we go, row column, it would be S12, S11, S22, and this would be S12, S21, so these two flip right here. And when they flip, the question you ask, are those two values the same? And they are, so it is a reciprocal network. Does everybody see that? Everybody with me on that? It's reciprocal. Is it lossless? This is the part you make sure you pay attention to. Is it lossless? It is reciprocal. Is it lossless? Is it lossless, class?
I feel like I got pretty good odds if I say no,
Why isn't it lossless? I asked that question.
because you have to take ST times S inverse or something? S
Well,
times-
normally, the way we do it, we would take S conjugate times S transpose times S conjugate, right? And if that was equal to the unitary matrix for a two-port system, it would be lossless. But here's a quick way to tell. If you look at a circuit right here, what's the one element that actually causes power to be lost? The resistor. Does it have a resistor in there? Yes. Is it lossless? Or excuse me, yeah, go ahead. Is it lossless? Is it lossless? No. No. And the way you can do that is just looking. Here's the one thing I want to tell you. When you make a circuit and you design it, there's a lot of things you don't see happening. And one is the parasitic type of problems that you have. And things can have loss factors, even though they're dielectrics. You can go ahead and make a circuit and you think it's pretty much lossless. And you put it in a network analyzer and you get a lot of loss, so you got a problem. Now, after this, now we're going to take care of a few more things. I'm going to try to work through some of the problems. I want to make sure I got this underway, and I showed you how to calculate return loss. By the way, what would the return loss be for this one? I didn't put it up here, but I will. For this problem, the return loss on port 1 would be equal to minus 20 times the log of the reflection coefficient on port 1. You have that? We know with this is simply equal to S11 right there.
Yeah, 9.63.
Minus 9 points.
Positive
9.6 what?
9.
That means it is causing a loss, if it's positive enough. And the insertion loss going from port 1 to port 2 would be equal to minus 20 times the log of S21. And what value do you get for that?
33.5.
That's about right. That's a lot of loss, by the way. A lot of insertion loss. That was for port 1 to 2. What's the insertion loss? Take a guess at this from port 2 to 1. Any takers besides you? What do you think? Tell me about S21 and S12. They were the same. If they are the same, if this is the same, if we calculate it for one, don't we have it for both? What is it? That is going to be equal to insertion loss from 2 to 1 would be 33.5 dB without ever doing a calculation because we know it's a reciprocal network. Finally, return loss for port 2 would be minus 20 times the log of really the reflection coefficient on port 2. It's matched, so what do you get?
0.009. This is about 1.
Okay. Something that bothers me about that. I'll get back to this one. That's the problem. That's this problem. Now we have to take care of things where we actually move what's called the, we're going to shift what's called the reference point. So pay attention to this. I'm going to slow down. By the way, has anybody looked at these videos on the internet that Steve's putting up? Can you see them all right? No?
I'm
Okay.
moving
Yeah,
forward.
you can see it?
Smith chart one I can see fine.
I couldn't see it.
Yeah, that's Smith chart. It's not more of an arm part of that, I think.
Thanks. I couldn't see it. I was too far away from the board.
But you can actually enlarge that to the full screen. And you should be able to see it. Maybe I'm wrong. That's a high def thing. You're doing 720, aren't you? Okay. Well, the next part we're going to do has to do with shifting reference plane. Now, if we have a standard S parameter network, right here, and suppose we have a length of line here, this is not hard to do, and another length of line here. If we have a network analyzer, you'll see where this is done all the time. Now, if we have that, as I'm drawing it here, and we have the length of line, this length of line is something that is non-trivial. In other words, you can observe it and measure it, okay? We're assuming we know what the electrical length is. It's not like 1/100th of a wave. Well, we're assuming it's got some appreciable value. So, I'm going to assume this has got some length L1. This has some length L2. Now, I want you to follow me on this and think about what I'm saying. When we have any kind of wave, and we have a transmission line, and it's propagating down the transmission line, right? The transmission line has some characteristic impedance Z naught. It also has associated with this beta. Beta is the phase number, right? Beta tells me how many radians per meter things change. You all agree with that? If we have that, if I take a signal right here, and I assume at this point I inject the signal and it is V1, or I'm going to call it, yeah, V1, at some angle 0 degrees. I want you to follow me on this. As the signal moves down here, the phase changes. Does everybody agree with that? Think about it. We could either call it a time delay, or we could talk about a phase change. We all know how to calculate the time delay if it's moving at the speed of light, right? It's just going to be the total distance traveled divided by c, the velocity of light. That would be the time delay. Well, the phase delay, this thing starts going back in phase. Or if this is at 0 degrees, I move this way. Well, the wave has to move this far down. So this part of the wave out here would be delayed by that length of phase. Does that make sense to everybody? If this is 1 at 0 degrees and I move 90 degrees down the line, it'll take another 90 degrees to get here. So if this is at 0 degrees, this would be at minus 90 degrees times the magnitude. How many see, at least in theory, what's going on here? So if I have a given length of line here, and I move down here and I inject, I've got some signal right here, some V1 plus. Well, it moves down here. The actual signal that's incident on this port right here would be equal to V1 plus, but then it would be delayed by e to the minus j beta times L1. Because now it's delayed by that much. Does everybody see that, class? We're going to assume that, or we can actually see this, we can see that this delay in this direction would also occur if the signal was coming from here and going this way. Does everybody agree with that, class? If you had a signal coming through here, instead of coming out of port 1, it would be delayed by e to the minus j beta L1 before it reaches this point right here. This will make sense to you in a second. How many see that? All right, it's not hard to understand what's going on. What about the phase delay associated with this length of line right here, L2? What would that be? E to the minus j beta times L2. And really, it depends if the signal's coming this way or this way. Now, where the signal is, or the phase is known for the signal. Is everybody with me on this? Now, our original S-parameter network, if we know the S-parameters of this network right here, assume we know them all, and I'll put them in. You're going to hate me for this, but go ahead and do what you need to do here. I'm going to say this is S11, S22, S21, S12, and I'm going to say those are known, right? I'm not trying to fool you on this stuff or just swamp you with information. We know that. We measured the device. We've got those parameters. Now we're after something where we want to move, and we want to find out what the S parameters here would be. Let's think about S11, what it is. It's the ratio of the voltage going in there to the ratio of the voltage coming out here, right? At port 1, right here. You all agree with that, class? What actually happens when we move here? Well, now, the S parameters here, it would be the ratio of this voltage. It would no longer be the voltage there. Well, this voltage is delayed by 90 degrees getting there, right? And as the reflected wave comes out of here, whatever is transferred here comes out, that's delayed by another 90. How many see that? Just think about this for a second. You should. If I send a signal here, it's delayed by 90 degrees by the time it hits here. How many see that? Now, think about that. That would be V1 plus, right? Wouldn't this thing be delayed by another 90 degrees when it reflects? How many see that? What's the total delay here? 180, or it would be minus j, well, we could say, it depends if that's 90 degrees, it would be minus j 2 beta L1. Do you all agree with that? So now what I can do for my S parameter matrix for this, now I can say the S parameters of this entire system here, and you'll see this, I can say that those S parameters are this. I can say S, and this is going to be shifted, S prime. Well, if I look in here, when I look into S11, I can see really, I take this value of S11 and I simply phase shift it by 100, or by e to the minus j beta, or 2 beta, beta 1 times L1. Beta 1 would be associated with this line. Now just think about this, because really S11 in generally is V1 minus over V1 plus when V2 is equal to 0. But that's assuming I'm right here. I measured it right there. Now I move out to here. Well, if I've got this value, it's really just going to be phase shifted by e to the minus j 2 beta L1. What do you think happens to S22? What if we look on this port? S22 is really measured right here, isn't it? Well, if we move right here, don't we take the incident waveform, delay it by e to the minus j beta, e to the minus j beta 2, you could say, times L2, right? And then it's delayed again on the way back. So here we can just say it's S22 e to the minus j 2 beta 2 times L2. The only reason I'm putting beta 1 and beta 2 here is if these two values for the transmission line, if Z0 is not the same or the velocity isn't the same, they would be different. Most of the time they're the same. And the test problems, they will be the same. Is everybody all right with that? Now what do you think happens here, S21 and S12? Think about the time of the phase delay. How much am I delayed from here to here? Now think about it carefully. Well, how much am I delayed when a signal comes in here and it gets to this port? It's what? E to the minus j beta 1, L1, right? You assume that there is no delay through this part of the network. In other words, there's no appreciable delay. Now, how much is it delayed through this part? E to the minus j beta 2 L2, right? And if betas are the same, really what I can say, I can say this. It's e to the minus j beta 1 L1, and I can say times e to the minus j beta 2 L2. If the betas are the same, I'm going to write down what that value is. Couldn't we do the same delay right here, class? E to the minus j beta 1 L1 times e to the minus j beta 2 L2. Now that's what the S parameters would be. That's one ugly drawing right there. But the actual S prime parameters, if beta 1 equals beta 2, would be equal to S11 e to the minus j would be 2 beta times L1 plus L2. S22 times e to the minus j 2 beta times L1 plus, or excuse me, this is just L1, and this is L2. This is equal to S1, or S21 times e to the minus j beta L1 plus L2. And this is S12 times e to the minus j beta L1 plus L2. I did it this way because in the real world, you might find the value of the transmission line feeding one of these networks being different than the value of the transmission line, the beta on the transmission line on the other side of the network. However, we're going to assume this for now. All right. That's going to be equal to the phase shift and the reference, or what happens when you get a reference plane move. Now, the reason I'm telling you this is because if we can, what we're going to do is we're going to take a look at Dr. Wentworth's network analyzer. We're actually going to see something that measures S parameters, and I have to check with him about this. But I'd like to have everybody see this if possible. How many have seen this already? 1, 2, 3. Three people out of the class. So we would like everyone to take a look at this. That way you know what device is used to actually measure this. Now we're going to take a look at one other thing. Don't worry, I'm not lying. What the time is. You might have a little trouble with this, and I did go through this kind of fast, but I think you'll understand it. Now, next thing we talk about, so far we've talked about just a two-port network. In general, you can have an N-port network. And let me just tell you, this, he talks about couplers and dividers in the next section. And this is really couplers, dividers. Now, when we do this, I'm going to show you why this is important. If we have a system, here's one port. It's got signals going in and out, right? Now I'm going to put something, and here's what I want to happen. Think of this as really something that's taking care of traffic flow on an intersection. There's roundabouts. You've seen all these different things. It's really the same idea, only we're dealing with electronic signals. Well, suppose I have a network here, or I have a port here and a port here. All these have characteristic impedance, some characteristic impedance. We're going to use Z0 right here. Just Z0, Z0, and Z0. I'm not showing you what's on the inside. I'll talk about that in a second if I have time. Suppose I want all of this signal right here to come out there. Got me on that? So I want everything coming into this port. This might be port 1, call this port 2, port 3. It's irrelative what the ports are numbered for this little discussion. I want everything that comes into port 1 coming out of port 2, but I want all the information coming in port 2 to come out port 3. Got me on that? Then I want all the information coming from port 3 to go in port 1. And you're saying, why? Well, radar uses things. The radar systems use this. They have something where the signal coming out of an oscillator goes one way and through the radar, and the system coming from the radar, if it's using the same antenna that's extracting the signal, they want that portion to go another way. You all see that? It's just directing traffic. Well, if I do that, I can do that by simply getting a 3x3 matrix. And now, I'm just going to put this up here, just write this down and move it on. I can say V1, V2, V3, minus, minus, minus. It will be equal to, now we're going to have a 3x3 S parameter network. This would be S11, S22, S33. These are all reflection coefficients, if it's matched. And then we have all these other things. S21, that's the forward transmission coefficient going from port 1 to port 2. We have S31, we have S12, S13, and we could fill this whole matrix out. Do you all agree, class? Real quick, and then you're gone. If I take a look at this, and I want all this stuff coming into port 1 to come out port 2, right? Now just follow me. This is all multiplied by V1 plus, V2 plus, V3 plus, right? Follow me here. Everything in port 1 coming out port 2. What does that tell you about the parameter? Take one look at this. I want everything coming, I want this to have all this information. Well, if I look at that, that would be V2 minus. Will you, class? If that's V2 minus, I want to make sure V2 minus will be this times this right here. So wouldn't I want this term, I would want this term right here, S21 times V1 plus to V1. You all see that? This would be a value of 1. You don't care about this value yet. And this could be a value of 0, but that's how we're going to get it. I know this was kind of erratic. You can go ahead and go. Next time, I'm going to go ahead and go through it. But remember, that's for directing traffic. I'll put some of the answers up. I hope you did good on your test.